Find the voltage across the capacitor. So initially the switch was connected to point A. Then at t equal to 0, the switch moves to point B and remains at B. Now Vs equal to V0 is a constant voltage source. Okay, so what we wanted to do here is to find the voltage across the capacitor for t bigger or equal to 0. Now, so when the switch, so before t equal to 0, okay, so before t equal to 0, this is the network, 200 ohm, and then we have point A here, have the capacitor connected to point A, and the voltage across the capacitor is Vc of t. So we need to find, so I'm gonna call it Vc of t0 minus, right before t equal to 0. Okay, so that means at t equal to 0 minus, right before the switch move to point A. Okay, so right before the switch moves to point B, point B. So right before the switch moves to point B, this is the network, and we know that this is equal to V0, right? It's a constant voltage. So in the previous video, we justify why the voltage across a capacitor cannot change instantaneously. So now because the capacitor is connected to point A for a long time, right? So because the capacitor is connected to A for a long time before t equal to 0, or before the switch moves to B, the capacitor will be fully charged. So will be fully charged, right? So please, if you haven't watched the first video, I highly recommend that you watch that video as well. So when the capacitor is fully charged, Vc of t is constant. Okay, so we justify this in that first video, right? So that means dVc dt equal to 0, right? We know the current IC equal to C dVc dt, so 0. So 0 current means, so 0 amps. This implies that the capacitor is an open circuit. Okay, so then let's redraw the network right before, so I call it t equal to 0 minus, right before the switch is moved. We have the 20 ohm 200 ohms, and the capacitor will be open. And then here we have the voltage VC0 minus, which is the voltage right before the switch moved to B, right? Voltage right before the switch move to B. Okay, so this is V0. So this implies that V0 equal to VC0 minus, but let's write KVL to justify that. So when I write KVL, I have V0 equal to Ri times Ohm's law, that's Ohm's law, and VC0 minus. So the current is equal to 0, so R times 0 plus the voltage across the capacitor right before we move the switch, so VC0 minus equal to V0. So let's say V0 is 10 volt. So that's 10 volt. So VC0 minus equal to 10 volt. That's the voltage across the capacitor before the switch is moved. Now, so when the switch moved to B, when the switch moves to B, okay, so the circuit is this. So we have the source, we have the 200 ohms, but then we have the capacitor now connected to the 10 kilo ohms and to ground. Okay, so the voltage across the capacitor is what we want to find. So 10 kilo ohms. Okay, so we know that the capacitor is a passive component, so the current flows from plus to minus. So I label the current IC of T that way. Now, when the capacitor is connected to the 10 kilo ohm source resistance, the resistance, all the energy will be dissipated by that 10 kilo ohm resistor. Okay, so when the switch is connected to point B, all the energy stored in the capacitor so will be dissipated as heat by the 10 kilo ohm resistor. And because the switch is connected to B for such a long time, all the energy will be dissipated, so the voltage across the capacitor will be equal to 0, because there's after quite some time that there's not going to be any voltage across the capacitor. So VC, so when the switch is connected to B for a long time, VC after some time will be equal to 0. So after 5 time constant, as we indicated in that first video. So, and we also know that the voltage across the capacitor is the final voltage plus the initial voltage minus the final voltage, e to the negative t over LC. So we know the initial voltage was equal to 10 volt, and the final voltage will be equal to 0 volt. So when I substitute that, and those in this equation have 0 plus 10 minus 0, e to the negative t over LC. So VC of t will be 10 e to the negative t over LC, and t is positive. Now we are told that R equal to 10 kilo ohms, C equals to 100 microfarad. So LC is 10 kilo ohm, sorry, 10 kilo ohm. So 10 times 10 to the 3 times 100 times 10 to the negative 6. So we have 10 to the 6 times 10 to the negative 6, which is 1. So the time constant, RC, equal to 1 second. Okay, so VC of t will be equal to 10 e to the negative t, t bigger equal to 0. So we can sketch this voltage. So VC of t. So 1 time constant, 2 time constant, 3 time constant, 4 time constant, 5 time constant, 6 time constant. So at t equal to 0, the voltage will be 10 volt. Then t equal to 1 time constant, what do we have? We have 10 times e to the negative 1. So 10 times e to the negative 1, we can calculate that. So let me calculate that. Let me pull my calculator. So we have 10 times e to the negative 1. That should be 3.67. So 3.67. So after 5 time constant, the voltage will be almost equal to 0. Okay. Okay, so that is VC of t. So in the next video, we are going to solve a network that's slightly more complicated. So for that video, we are going to find the equivalent resistance seen by the capacitor. So here we have a series network. So it's easy to solve. But when we have other resistances in the network, then we're gonna have to combine simplify the network down to a series network, right, to be able to find the total resistance seen by the capacitor, and in that way we will be able to calculate the time constant. So thank you for watching.